Hi, my name is Timothy King. This semester I'm doing an exploratory research project on the linguistic component of answering short answer questions, comparing ChatGPT performance to that of humans. For background, there are several instances of instructors and technologists observing ChatGPT's performance on various tests, some of which we will go over in the next slide on related works. Maybe you've seen some of these before, like ChatGPT being able to pass the bar exam. One of the intermediate steps of question answering is natural language understanding. For a large language model, the ability to perform natural language understanding is heavily dependent on the features of the question or prompt. It's been observed that even small alterations to the design of a prompt can have a big impact on the language model's ability to perform on specific tasks. Linguistics, as the framework by which we understand language, provides us with lexical, syntactic, and grammatical parameters, which in turn can help us inform prompt design. So the main research question that I am exploring is, what linguistic trends emerge that correlate to better short answer performance? How does sentence complexity, sentiment, and ambiguity perfect performance? How significant are existing correlations, and what recommendations can be made from them? So for related work, we have a number of instances of researchers testing out capabilities of ChatGPT on exams meant for students, including a medical licensing exam, math and reasoning problems, physics problems, and even one instance where students were asked to act as the intermediary to take tests for which they had no prior knowledge, while using ChatGPT as their only resource. And in that specific study, the students did not actually perform well with the use of ChatGPT. Some other relevant works important to this project are that although ChatGPT will imitate specific linguistic traits like its reuse of sentence structure, disambiguation of certain words, and identification of thematic structure, language models will exhibit some differing linguistic qualities than humans, especially in writing. In some places better than human performance, in some places worse. And features that are present in the writing of prompts can impact responses. For instance, ChatGPT will often produce longer responses to prompts that have negative sentiments. So given this, let's take a brief look at some of the linguistic features that have the potential to produce trends in this exploratory analysis. The first category of analysis is syntactic measurement, which deals with sentence-level analysis. These include sentence complexity, structure, and arrangement, as well as the length of a given prompt or test question. The second category is the lexical features. These are the word-level measurements. They include word frequency analysis, or more generally, the word popularity or rarity. It also includes information about word morphology, so like, do words in the prompt include prefixes or suffixes different from the stemmed or lemmatized form of the word? And do these words contain distinct inflections or tenses? Also, what can be known about a word's meaning or level of ambiguity? The third category of additional measures that includes sentiment and subjective language measures, the grammatic quality of the questions, and if there's time, I would like to perform qualitative analysis of some of the higher level concepts often discussed in prompt engineering, like the presence of sufficient context or framing of the prompt within adequate scope. Here's the data set. It's not a comprehensive data set. There are just under 150 samples. It contains the question, the course subject, the type of test it was featured on, the maximum points one can earn for a question, points earned by a student, and then the points earned by ChatGPT. The answers were graded personally by human subjects. If we take a look at the first question, we can see that it is a logic problem from a discrete structures class, and both the human subject and ChatGPT received full marks on the problem. For simplicity, I created 2 additional columns for measurement of performance. The first is simply a column making all the problems worth the same by dividing ChatGPT's marks by the maximum marks. The second column was a measurement of comparison, measuring the difference in score for the human subject and ChatGPT, as shown in this formula. As a point of comparison, here are 2 graphs. The first shows ChatGPT's performance for each of the subjects in the dataset, and the second one shows the delta value, where less than 0 means poorer in comparison to human, and above 1 means better than the human subject. There is some overlap between the two graphs, but they are definitely not one-to-one. Maybe more notably, we can see that ChatGPT scored quite well on most questions, which will definitely be important to discuss in the later analysis sections. The first piece of analysis that I have to show is for the sentiment analysis. Here I measured sentiment polarity of the questions using spaCy and TextBlob NLP libraries. I then graphed this sentiment measure by the delta values to see if I could visually see any patterns. There's generally a normal elliptical spread of the data, with some exception, which is more clear to see with this contingency table. The table categorizes both the sentiment and the delta score values into negative, positive, and neutral or 0. Here we can see that a question with a negative sentiment produced a worse score than human subject only one time in all the samples. And this is statistically significant in comparison to expectations. If we look at the ChatGPT scores without the human comparison, we also see only one instance where a negative sentiment produced a less than perfect score on a problem. Another sentiment measure I looked at was related to subjective speech. I again calculated this with spaCy and TextBlob. This measurement ultimately did not produce any meaningful correlations, and a visual inspection of the data confirms that there is no meaningful trends that might require additional analysis to uncover, nor is there a need to resample the data set to account for the skewing towards 0 values in this particular case. The next form of analysis is the quality of grammar. For this, I used the language tool Python's grammar checker that counts the number of errors per question, generally falling between 0 and 3 errors. For this table, we see a consistent distribution among perfect and non-perfect scores. This holds true for the average scores for each of the errors, and it's also consistent for the delta comparison as well. This suggests that minor grammar errors did not have a meaningful impact on the performance. Next, I looked at sentence length, simply counting the number of tokens per question. Here's a plot of the length to relative scores. There aren't any clear trends, but I did transform the data into a histogram because I noticed that smaller sentences might have caused more variance. That can be seen a bit in the plot showing the sentences between 4 and 8 words, but this was not found to be statistically significant, so it can't be a proven trend of the data. The final two types of analysis I have to preview are the morphology feature counts and syntactic complexity. Morphology changes were counted using NLTK's stem and lemmatization tools, and following the Herbold paper, I calculated a measure of syntactic complexity using spaCy. After graphing this data, I immediately recognized the similarity to the token count graph, and their apparent correlation makes sense. The more words means more word changes on average, and similarly for sentence complexity. So for these measures, I mostly looked at them relative to their token lengths. For morphology changes, here they are grouped into 3 categories based on the number of changes per word. There's a slight negative trend visually that can be seen a little more clearly with the average score values, but by correlation tests, this occurrence does not have a small enough p-value for it to be proven as a trend of the data. The syntactic complexity measure was also split into categories, and there's one small outlier for the overall scores, but as we can see here, this also was not meaningful enough to be statistically significant. So that was what I have to show for right now. My results are a bit more preliminary because I switched to this project topic only a few weeks ago due to a data collection issue with my first project idea, but I have been working on several other forms of analysis, which are the primary focus of this project, but I have not been able to finish them in time for this milestone. Here are 3 of the things that I'm continuing to work on in the next couple of weeks. The first is sentence arrangement analysis. Arrangement refers to where ideas are located in a sentence. Sentences can be arranged in balanced, loose, periodic, or cumulative. There's no out-of-the-box solution to measure this, but I am working to build a method using tools like spaCy, Stanford Core NLP, and PropBank. The The second kind of analysis I am working on is the use of tools from the NLP for the Social Sciences suite. These tools are frequently used when measuring linguistic features in EdTech research, such as papers on language learning tools, automatic essay graders, or the usability of generated textbooks. There are also tools for the automatic measure of lexical diversity, readability, text complexity, and text cohesiveness. In their standard form, these tools exist as applications that take text files as input, but they have recently been converted into Python packages, which is more useful for my given dataset. Right now, I've not been able to finish this type of analysis because the Python implementation requires a dependency that does not work right in my current environment, but I should be able to have this up and running pretty soon. The third type of analysis left is word frequency analysis. This is not a measure of the repetitions of individual words in a prompt, but rather looking at global popularity metrics for individual words used in prompts. For this, the English Corpora has a word frequency tool that ranks a large number of lemmatized words. I am trying to use this tool because it's the most accepted way to perform this kind of research, but as a backup plan, I have written a simple web scrape for the Google Ngram Viewer tool, which runs on a massive dataset of Google Books to do the same task. So because I did change my project somewhat recently, I would like some feedback on things like the framing or scope of the project and the progression from the research questions to methodologies, since I didn't showcase those things in my first intermediate milestone. Additionally, I would love to hear any feedback, criticism, or comments on what I have previewed so far and the methods I plan to pursue in the next couple of weeks. And here are my references. That concludes my presentation. Thank you for listening.